Way back in Chem 1A, you learned about reduction and oxidation chemistry. I always struggled with keeping track of what is being oxidized, what is oxidizing, what even is an oxidation number. Pretty much everything about redox chemistry confused me. So I want to revisit these concepts, especially since it's been a while for you, and we'll need a good grasp of this going into electrochemistry. Oxidation reduction reactions, or redox, involve the movement of electrons. An example of a redox reaction is hydrogen gas reacting with elemental sulfur to form hydrogen sulfide gas. It helps here to have the Lewis dot structure of each of the chemicals drawn so we can see where the electrons are. In this reaction, electrons move away from the hydrogen atoms and towards the sulfur to form the final product. Because sulfur is gaining electrons, sulfur is being reduced, and in turn, hydrogen is being oxidized. A common mnemonic used is LEOGR, like a lion goes grr, which is short for loss of electrons is oxidation, gain of electrons is reduction. Rather than comparing Lewis dot structures and figuring out electron movement, a more quantitative way to look at redox reactions is through oxidation number. Oxidation number is kind of like ionic charge for individual atoms within a whole molecule. This is not the same thing as calculating formal charge, where electrons and bonds are equally shared between atoms. Instead, we determine oxidation number through a variety of contextual factors. So just like the charge of a complex of polyatomic ions and neutral compounds, the sum of the atom's oxidation numbers must equal the charge of the whole molecule. Chemicals in elemental form, as in all made up of just one element, like O2 or S8, have an oxidation number of 0. There are also quite a few elements that have well-defined oxidation numbers when in a polyatomic molecule, mostly determined by whatever group on the periodic table they're in. Like groups 1 and 2 elements have +1 and +2 oxidation numbers, respectively. And a group 2 or group 7 will usually have -1. Also, oxygen in a polyatomic molecule will usually be -2 in oxidation number. So looking back at that earlier example, let's see how the oxidation numbers for each atom change in the reaction. H2 is elemental, so hydrogen starts with an oxidation number of 0. Monatomic sulfur here is also neutral, so it's also 0 to start. In H2S, however, hydrogen, being a group 1 element, has an oxidation number of +1, and sulfur, in group 6, has an oxidation number of -2. Comparing before and after the reaction, we see that hydrogen increases in oxidation number, as in it's oxidized, and sulfur decreases, so it's reduced. Another way that chemicals in redox reactions are often denoted is by reducing agent and oxidizing agent. So let's see here. This is just describing which chemical is doing the reducing, i.e. the reducing agent, to the other chemical, i.e. the oxidizing agent. I know it's a little confusing and sort of in the passive voice, but to be clear, the reducing agent does the reducing and therefore gets oxidized. And the oxidizing agent does the oxidizing, getting reduced. So putting it all together, I've listed out all of these different traits or names of the chemicals involved, and they really boil down to one thing: where the electrons are going. Imagine we take the example reaction from before and break it up by atom. Like S with oxidation number 0 gains 2 electrons to form S with oxidation number -2. In the same vein, H2 neutral forms 2 H+ plus 1 and 2 electrons. These are called half reactions for obvious reasons and are how we can simplify a larger reaction into its component parts. Because S0 is getting reduced in this half, that is called a reduction half reaction. And likewise, the hydrogen half shown is an oxidation half reaction. The appeal of splitting a reaction into its half reactions is that each one of the half reactions has a potential associated with it. Essentially, this potential is the amount of energy required to make the electron transfer occur, and is in units of joules per coulomb or volts. Most of these reaction potentials are well documented and can be found in a table somewhere in your book or online, but for simplicity's sake, we're limited to standard reduction potentials, or E0. I found that S0 to S minus 2 has a standard reduction potential of negative 0.48 volts, and that 2H plus to H2 has a standard reduction potential of 0. Now, you'll note here that I have to refer to hydrogen's standard reduction potential, even though hydrogen is being oxidized in this example. So to actually capture the potential for the entire reaction, I'm going to add E0 of the species being reduced, i.e. sulfur, minus E0 of the species being oxidized, which is hydrogen. Lucky for us, hydrogen is the baseline of standard reduction potentials, so E0 of this reaction is just equal to E0 of sulfur, or negative 0.48 volts. Let's look at just one more example really quickly to make sure we've got this straight. So solid lead and aqueous cadmium-2 react to form aqueous lead and solid cadmium. The two half reactions here are solid lead producing aqueous lead and 2 electrons, and aqueous cadmium picking up 2 electrons to form solid cadmium. The lead here is losing electrons, so it's being oxidized. And the cadmium is gaining electrons, so it's reduced. The standard reduction potentials of these are negative 0.13 volts for lead and negative 0.4 volts for cadmium. So the total potential of the reaction is E0 of reduced minus E0 of oxidized, or 0.4 or negative 0.4 volts minus negative 0.13 volts, which is equal to negative 0.27 volts. In the next video, we'll talk about how these reactions are utilized in the modern world.